All right, so the recording should be in progress. Welcome, Marcus. Hi, everybody. Hey, Mirko.
Oh,
Okay.
okay.
So the stage is yours,
Mm,
right? Okay.
Yeah. Okay. So for this last seminar, I wanted to talk about discrete Wigner function, and basically why it's not working for qubits and how it can be used for arbitrary qubits. Basically, the idea is kind of similar as in the bosonic case. And actually, the first thing that we need to observe is that the while operators that we introduced last time form an orthonormal basis. So is an element in the discrete phase space. So this is well, actually, it's an orthogonal basis with respect to the Hilbert-Schmidt product. So, namely, take two while operators, and this product is defined to be the trace of WA dagger WB. And this is actually, you can see that this is basically proportional to W B minus A. And that's because WA dagger is just, you just need to invert the sign of the point of the phase space point. And this trace here is basically the identity because these operators are, it's the trace of the identity because these operators are traceless, except the identity. However, it's a little bit simpler to define a Wigner function with another basis, with respect to another basis. Namely, we just rotate things and we introduce the phase point operators, which can be seen as just operator associated to every point in the phase space. And to introduce them, we consider the character of the base field in the usual way. So this is just something like e to the I 2 pi over p. And these operators that are usually denoted with a are defined in the following way. We have a dimensional factor, and then we take the sum over all points in the phase space, and then there is this character here evaluated in this symplectic form, and then there are while operators. And these operators form another basis in the space of operators we are considering. That means that we can decompose any operator in this basis, and so basically for any x we have the following decomposition. And here we have some coefficient associated with x, and then we have the phase point operator. And this coefficient here is the discrete Wigner function. Just to, since usually one can define the Wigner function as a Fourier transform of the characteristic function, this is exactly the same thing, because by definition, this Wx of A is just the trace of A times X. Should be A dagger, but these operators can be verified are Hermitian. And if you expand everything, now you have 1 over p to the n, and then there's just the definition of the phase point operator. So we have the sum over b, and then we have chi of ab, and then there is the trace of w b x. Yeah, this trace here is the characteristic function, and when you take the sum and this with this coefficient here, this is a discrete analogous of the Fourier transform. So it's just the same definition. Okay, that's the basically. Yeah, I'm going quite fast here because I think it's kind of standard what is done here. And actually, even the properties of this discrete Wigner function are basically the same that you have in the bosonic setting, and they can just be verified by definition, by the definition. So I want to just to list some of them. The first one is that you can evaluate the overlap between two operators with respect to the trace inner product, and this is just the sum of the corresponding inner function over all phase space points. One is complex conjugated. And this, if you consider this Wigner function on states or in general Hermitian operator, this is a real function. Basically, you have this. Of course, it's not always non-negative, so it cannot be seen as a probability distribution for arbitrary operators. And yeah, basically, you can also rewrite the Born rule in this language. To do this, you just need to give a Wigner description of, if you want, channels and POVMs. So for a channel, well, it's just a super operator. You will have the following description in the Wigner language. So you have the inner product of A with phi evaluated on A of B. And if you have an element of the POVM, you have that W of A or the WE of A. It's just these other inner products. And so the Born rule is just take everything together. So if you want to write the following probability given a state rho, you just have the sum over all phase space points. And then there are all the Wigner functions. So yeah, the Wigner function associated to the operator E, the Wigner function associated to the quantum channel, and lastly, the one associated with the state rho. And this last equation is basically what you can use to do some simulation using Monte Carlo methods. And I'll just came back to this point later on. But given these basic properties, now we distinguish between odd and even characteristic as always. so starts with p not equals to 2. And in this case, we can derive, well, I will not prove, but that they are the only states with this property, but we will see, we can see that stabilizer states have a non-negative representation. To do this, we consider a Clifford gate. And just remember that these operators can be written as a product of two operators. We have a while operators and then an operator associated with the symplectic matrix. So G is the symplectic group, and B is still a discrete phase space point. And now one can start from an operator, from a phase point operator, and see what happens when you conjugate that with the Clifford operator. So we have this W and mu acting on A, and okay, so we just need to, we know the action of W and mu on while operators. So just we just expand the definition of A. So we have P to the minus N, and then there is the sum over phase space points. And now there is a W of GB, and this comes from the action of mu. Then there is a chi of AB, and this is still from the definition of the phase space of the phase space phase point operator. And finally, when you conjugate with W of B, you get another of these phases, and namely this is just chi of BGB. Okay, and then now we can just play around with these characters. So this is P to the minus N, and then we have the sum over B. Okay, so then we have this chi bar of A, G to the minus 1 B, chi of VB, W of B. So we just send B to G to the minus 1 B in this step. And then we have P to the minus N, and then the sum over B of chi, and then we have GA minus V, B, W of B, and this is just by property of the symplectic product, because yes, that's when AB is equals to GA, GP, when you have a symplectic matrix. But now we have again basically phase point operator, but translated. So this is just A of GA minus B. So when we act with the Clifford operator on a phase point operator, we just we obtain another phase point operator but acting on a permuted phase space point, and this is just the Clifford covariance of these operators. And that means that the negative, yeah, it's like when you go on the Wigner function level, the negativity is not changed. So let me write this maybe. So yeah, the negativity is which is defined as basically the L1 norm of the Wigner function, and which is a quantity greater than 1, is not changed in this case. Now we can apply this to stabilizers. So remember that in the case of stabilizers are basically described as projectors over on some subspace, where this is a Lagrangian subspace of the phase space, and these were defined in the following way. So we have sum over L, and then we have the character, and then HL WL, where this H is a phase space point. And then, yeah, given this definition, and this is basically an object projector this 4, we can just evaluate first the characteristic function. So we have the trace of WA as S. But then everything goes out of the trace, and then we have the trace of WA, WL, and they are traceless. So this is basically P to the minus N, and then we have the character HA, and then we have the indicator function on the Lagrangian subspace that determine our stabilizer state. And so that means that when you go to the Wigner function associated with this state, this is, yeah, well, just rewriting the definition for clarity. So we have this transform.
Mirko, I think the dimensional factor in the trace should not be there, because you get a trace of the identity.
Yes, probably you're right. Let me double check, but
because this one sub L is the indicator, right? It's not the identity.
Yeah, it's not the identity.
But otherwise, so far, I think everything looking good to me.
Okay, yeah, probably you're right. So let's cancel. No, this is correct. The other one's not. And okay, yeah, nothing. And then we have the trace. Yeah, well, we have the characteristic function. Just plugging this characteristic function that we have above. So this is P to the minus N, and then the sum over B. Now chi of AB, chi of HB, and then there is the indicator function of B. Okay, this sum here is still on the whole phase space, but since here we have the indicator function, we can just collapse the sum over L. only, because otherwise everything is 0. So we have the sum over B in L of the basically the same thing. Okay, and this is the indicator function over A minus H, or you can also rewrite that as the indicator function over L plus H or A. But yeah, the main thing here is that basically this object is non-negative. So yeah, in the odd case for stabilizers, we have a non-negative representation in the Wigner formalism. And actually, for pure states, they are the only states with this property. And this is the Adston theorem proved right now 20 years ago at this point. But this holds only in odd characteristics. But anyway, given this theorem, we can basically use this for simulation. And yeah, it's basically, if we go back at this equation here, because at this point, if everything is, if we look at this equation and everything is non-negatively represented, then we can use this as a tool to do some Monte Carlo simulation, where we look at where these objects here would be transition probabilities. And yeah, basically you can sample from this quantity here efficiently. I mean, this stuff here, and then you can just do some, you can just define an empirical average for your state to do simulation, and this can be controlled with some bound, and yeah, basically your sample complexity is not going crazy. The advantage of this kind of simulation with respect to the Gutzmann-Neal theorem is that here, well, Gutzmann-Neal basically is not really working when you consider, yeah, when you have, for example, quantum channels, right? You can just do unitary evolution there. And while here, yes, if you have some noise, given that your description is positively non-negative, you can still do this kind of simulation. Yeah, and when you don't have this condition, so something here can be negative, then your sample complexity basically grows up a lot, and what controls your sample complexity there will be the negativity of the Wigner function. Yeah, that's the difference. But the idea is, just to recap, the idea is that you can interpret this as something like sum over AB of an object and then a probability distribution, and then you can sample from this probability distribution to and then you can construct an empirical average for X. And yeah, it's just this note. And of course, yeah, if you have many channels, then you have just the composition of many channels, and but conceptually everything is the same. And the last thing that I want to tell you about this Wigner function stuff is the event case where everything is not working anymore. And that's because when we discussed the event case, we had additional phases, right? So the idea is that in this case, if you have a stabilizer rho, this is something like 1 over 2 to the n, then you have still the sum over all vectors in the Lagrangian subspace. And in this case, the character has the form of -1 to the hv, but then you have an additional phase, which is not nonlinear, and then the value operator. And yeah, so the thing is, in this case, well, you can do the same thing as we have done here for the characteristic function and the Wigner function. But yeah, it's like you have this additional phase, and that means that basically there exists stabilizer states which are negatively represented. And another consequence of this additional phase is that the Wigner function associated to a stabilizer state is not Clifford covariant anymore. It's kind of, yeah, I'm not writing any equation here because it's literally the same calculation, but then every time here you will have this -1 to the alpha of b that will break thing. And yeah, and apparently, well, without apparently, actually, one idea to construct a discrete Wigner function for qubits would be to find a different Clifford covariant operator basis instead of the phase point operators. But actually, it was proven a few years ago that in the case of qubit, yeah, or a multi-qubit scenario, this is not possible. So yeah, that's kind of the end of the story, at least for what I know about qubits and discrete Wigner functions. And I will stop here. Yeah.
So what's the smallest n so that the qubit case fails? I guess for a single qubit you just flip, so maybe that would still be Clifford covariant.
Single qubit still works, but for more than 2 it breaks.
More, and for 2 it also works, or just
no? For including 2 it breaks. Yeah.
Yeah. So okay, so it immediately breaks. Okay.
Yeah, this is actually a cool no-go result by Huang-Chun Zhu. He basically showed that like any operator basis which is covariant under a free design does not exist basically in this dimension. Yeah. So there's basically only like 2 ways to circumvent that. Either you make your operator space smaller. So because it only holds for the for bases of the full operator space. So you can consider subspace of the operator space. Then if you choose the subspace small enough, then it works. This is like what people have done with these like rebits, like the real qubits and stuff like this. And or the other way around is basically that you go to an overcomplete basis. basically, then it also works. And that's the, I don't know, do you want to like talk more about this, Mirko, now, like about the second way out?
Yeah, I don't know. Yeah, we'll just see. Right now, I'm finished with this Wigner function stuff, and I don't know now what you want to talk about, Mark. If stabilizers, sorry, robustness or